Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Good morning, students. Happy New Year to you all. So, in our last class, we have started organic chemistry and some very important points we have learned about it. And what was the first of the definition of organic compounds or organic chemistry is what? The carbon can make compounds with hydrogen and some heteroatoms like phosphorus, sulfur, oxygen, nitrogen. And so these compounds, all the compounds in which only these elements are involved, they are all organic compounds and their chemistry is what we call organic chemistry. And the chemistry we know the bond breaking, bond formation, this is what we know in the chemistry and we studied. The general thing, what is the very important point about the carbon that we have also studied in chemical bonding and also in the some other chapters. This is what the tetravalency of the carbon. The tetravalency means the carbon can have four covalencies, and this is what is very important rule because carbon follows octet rule very strictly. So, in all the compounds of carbon, what we should actually take care of, the carbon must have four covalent bonds. And these four covalent bonds are very important. For example, if this is methane, means in methane, what we have seen, carbon has four covalent bonds with four different hydrogen atoms. And and in this case, we have seen the similar thing. Although the four covalent bonds, but three covalent bonds with three hydrogen atoms and one covalent bond between carbon and carbon atoms. And this is the same thing that we see here. In this compound, what we see, carbon has two covalent bonds with two different hydrogen atoms and a double bond with another carbon atom. So again, it has a four valency. So this is what we call the tetravalency or the covalency of carbon. This is very important point for us to remember because in many representation of organic compounds, if you do not remember that carbon should have a four valency, then you will actually always be in confusion that what is the real structure of this compound, and we will see what are different representation of organic compounds. And another important point what I have taught in last class is hybridization of carbon in different organic compounds. And what are the some general rules we have to hybridization and VSEPR theory, these things we have already seen in chemical bonding. But here what you should remember, if you don't remember those things, if carbon has forms all the bonds of carbon are single bonds, then the hybridization of carbon is sp3 hybridization. If carbon has one double bond, any carbon atom, if it has one double bond and the rest of the bonds are single bonds, so what then only two bonds will be the single bond. For example, this compound, one double bond and two single bonds, then the hybridization of this compound will be sp2 and this molecule should be the planar one. This kind of molecules should have the tetrahedral symmetry or the tetrahedral geometry, that is a better term to use here. So, and since it has some symmetry, so that's why I said. And now, if the carbon has one carbon has two double bonds, means one double bond here. If there is another double bond here, then in that case there will be no CH bond. So, what will happen? Then the carbon will have sp hybridization. Or else, what we see, if the carbon has one triple bond, if it has one triple bond, then also we see carbon. Then we see carbon has sp hybridization. And why they are so, I have explained this in last class. Another point is the pi bond and the restricted rotation or the hindered rotation around a pi bond, and that we saw when the pi orbitals, two pi orbitals or two orbitals with one electrons, they are parallel to each other. They form there happens overlap A1, two types of one overlap above the internuclear axis, and the same overlap happens also the below the internuclear axis that we see here. Overlap above, overlap below, and if we want to rotate this part of the compound slightly, it means what you are doing, you are changing the orientation of relative orientation of these two p orbitals which were overlapping. And while rotating, what will you are actually trying to break this bond, means you are trying to reduce the overlap. And once these orbitals will be at 90 degrees, there will be no overlap between them, so there is no double bond. So that double bond will break. Means to break this bond, to rotate this part of the compound with respect to this bond even by 90° by amount, you have to break this double bond, and that is why the rotation about a double bond is called a restricted rotation or hindered rotation, because you have to break that bond, and to break that bond, that much energy you have to provide from outside, and that is why the again this point, the restricted rotation around the carbon-carbon double bond, and it has certain implication in isomerization and some other chapters as well when you will see chemistry of organic compounds, and somehow one can calculate sigma bonds, pi bonds. These are very basic things that we are seeing. Now let us start the structural representation of organic compounds. A structural representation, whenever we talk about, these are also representation, structural representation of organic compounds that we have seen. There are many representations we have seen. This one can also represent organic compound in this form. These are also representations. So there are many different ways of representation of organic compounds. Some are very basic and very well known. So, and these are complete, condensed, and bond line structural formula. Nowadays, bond line structural formulas are more general and it's most commonly used in organic chemistry. But there are ways the complete structural formula one can write, or condensed structural formulas are also important and they are also used. Complete structural formula people usually avoid to write, because though it is right way to represent the compound, but I think it will take lots of time, and so to reduce the time to write a structural formula or a structure of an organic compound, people generally avoid it. But one should understand all these structural formulas, the ways of representation of organic compounds. So what we know, the structures of organic compounds are represented in many ways, is what I have said. One is the Lewis structure or Lewis dot structure that we have seen also in chemical bonding chapter, and where what we see the Lewis dot structure, we can change, or the one can use the same formula, and instead of dots or the electrons, one can use dash to represent bonds. So that is also the dash structure that we call. So Lewis structure is also we call the dash structure. Then the condensed structure, we will see what is the condensed structure, and bond line structural formula are some of the most commonly used representation. In the Lewis structures, what we see, one can simplify that Lewis structure. Instead of showing electrons, one can show if two electrons are there in the bonding, in the sharing between two atoms. One can use one dash to represent a bond, and where that bond means there are two electrons shared between these two atoms. And if there are four electrons that were shared between two atoms, then what will show? Four electrons means two bonds. So one can show two double dash, and double dash means double bond. So there is a double bond between two atoms, and so on. And if there is three dash between two atoms, that means a triple bond is between these two atoms, and it means that six electrons were shared between these two atoms. So the Lewis structure can be simplified by representing two electron covalent bonds, and we know two electron covalent bonds. Covalent bonds are two electron bonds, and that we call bond pair, and that bond pair one can represent as dash. Such a structural formula focuses on electrons involved in bond formation, and since in organic chemistry this is what is our importance, to show the bonds involved, electrons involved in bond formation, and then that one can represent using even a dash, and that understanding is already there. This one dash means there are two electrons, it represents two electrons. So a single dash represents a single bond, and single bond is two electrons. A double dash represents double bond, and triple dash represents triple bond, and triple bond is six electrons. So each dash represents two electrons, so six electrons, and the examples are here. So the lone with this complete structure formula, this is the of ethane, and what we see here, the carbon single bond, and this is such things we have seen earlier as well. Single bond means there is two electrons between this. Each carbon shares one electron with each other. Single bond between carbon hydrogen, they are all, this is what is a complete structural formula that we call. Now if the molecule is ethene, there is a double bond between two carbon atoms. Then we show two double dash between two carbon atoms, and this dash which are parallel to each other, the dash lines, and then two hydrogens are there, and these hydrogens, while writing, we usually what we try to show that this bond and bond angle, this bond angle, this bond angle, this bond angle should be in representation should be equal to each other. This is what we try to write while writing a structural formula wherever there is a double bond. Even if you do not write to represent this structure, that is okay. Even if you write one hydrogen here, but because these are just representation, they are not a structural. This structural representation do not show exact geometry of the organic compound. That is why one can the bond angle showing angle exactly equals to the experimental value is not important. And now the triple bond that you see, triple dash a triple bond. And this is a ethyne that we know. CH, and what is another point that I have said and important to be noted here is carbon is showing 4 valence in all the compounds. Carbon, one single bond here, one single bond here, one single bond here, one here. So 4 covalency. 4 covalency means 4 electrons. Carbon shares 4 electrons with 4 different atoms here, and because of that, it actually in the sharing it also accepts against 4 electrons, so its octet is complete now. This carbon has a similar story, and so its octet is also complete. Now, if you see this molecule, so carbon, there is a two single bonds between two. The carbon has two single bonds with two different hydrogen atoms. So 2 and 2, 4 electrons one can say, and 2 electrons. So it's the two valency. Second valency, it should have two valency, which should be completed with this carbon atoms, and that is why there is a double bond between them. A triple bond, again you see 3 bonds and 1. So the tetravalency of carbon is complete in all the compounds, and that is what is very important. And this structural formulas can be condensed by omitting some or all of the dashes, and this is what the condensed structural formula, that is what we say. So one can condense these bonds. Even if I say these compounds, if I represent this portion as CH3 and this portion as another CH3, so CH3 dash CH3 will be a condensed formula. CH3 dash CH3 or H3C dash CH3. Why H3C? If you write H3C, then one can clearly understand that there is a bond between carbon-carbon atom. Even if someone writes CH3, CH3, then you should have this understanding that hydrogen cannot have more than one covalency. If there is a carbon atoms in both the CH3, CH2, both the group a smaller group, both the groups do not have complete valency, means one valency is completed because of the bond between the single bond between these two carbon atoms. And this is what understanding you have to make from yourself. So CH3 is a condensed formula, or CH3 dash CH3 is also a condensed formula. So CH3 one can write this is what CH2 double bond or double dash CH2 double dash CH2 or H2C double bond or double dash CH2. This is also a condensed formula, or one can write H2C CH2 or CH2 CH2. That is also okay. I mean CH2 CH2. What does it mean? It means you have to understand from the formula that each group CH2 means the carbon has two bonds with two different hydrogen atoms. Both the carbons have, and both the carbons have two valencies that were unsatisfied, incomplete. So what it means? It means that there must be a carbon-carbon double bond, because carbon should have a tetravalency. Means all the carbons should have tetravalency. That means again that understanding you have to you must have. Then in this case, one can also have a condensed formula for this. This is HC triple bond CH or CH triple bond CH, or one can write simply CHCH. CHCH also means the same compound, and this again it means you have to understand in that case if someone has written CHCH, then you have to understand that there is a triple bond between two carbon atoms, because again CH, if I am writing CH means carbon can have only single bond with the hydrogen atom, and both the carbon has one hydrogen, so one valence is only completed because of the hydrogen. So three valences were left unsatisfied, and that must be completed because of the another carbon and because of the bonding with or the sharing of electrons with another carbon atom. So it means there must be triple bond between two carbon atoms, and then only the valency of carbon will become 4 in CH, and this is what is important for us to understand. So these structural formulas can be further condensed by omitting some or all the dashes representing covalent bonds. So one can remove some dashes, like I said, CH3 bond, CH3. Some of the dashes, or by removing all the bonds, you can like CH3, CH3. One can do the same thing as well, similar thing as well, by indicating the name of identical groups. And what we'll do that we identical groups if we are there. So if identical groups, if there are more than similar groups, then one can use subscript to represent them as well. The example that is here, what does it mean? If you look at this compound and this compound, what is CH3, CH3? The complete structural formula will be what? C, one hydrogen here, one hydrogen here, one hydrogen here. This hydrogen will be here, and C hydrogens will be one here, one here, one here. Similar things one can write. This is a condensed then one can condense it, and while condensing, what can we do? Three CH3 groups are attached with this CH group. And what can I write? CH3, CH3, CH3. All the CH3 I can write thrice CH. That is the condensed formula. That condensed formula is but one can also write it in this way. CH3 and this CH3 one can write, or this CH3 twice CH. Or there is another way to write CH3, CH, then this CH3, which is a side chain, one can write as in the bracket CH3, CH3, or CH3. So there are many ways one can represent this. I hope you understand this point, or maybe with the examples you will see later on, you will make this understanding clear. Now this example, if you see other condensed structural formula of ethane, ethene is shown here. One can represent this ethene also as CH2, CH2, and ethane also as CH, to complete it as a condensed structural formula. Now this example, let us see this example, CH3, CH3. One more point that I forgot to mention is the presence of heteroatoms. Organic compounds can also have heteroatoms like oxygen, nitrogen, as I said, sulfur, phosphorus. This kind of heteroatoms may be there in the organic compounds, and so such a and these atoms, heteroatoms, usually also have the lone pair of electrons. And lone pair of electrons, sometimes people may show those lone pair of electrons on the heteroatom. You may not show if it is required for certain understanding. Then you show the lone pairs of electrons, and if it is not required, and usually we show those lone pairs when we write the mechanism of organic reactions. Otherwise, it is not important to write lone pairs on those compounds, and that is why lone pair of electrons on heteroatoms like oxygen, nitrogen, sulfur, even halogen may or may not be shown in those compounds. And what are the heteroatoms? I think I have mentioned it last time. Other than carbon and hydrogens, what we see, compounds of carbon and hydrogen, only carbon and hydrogen, they are called hydrocarbons. And if in an organic compound, any other element comes other than carbon and hydrogen, that atom is called heteroatom. And usually in organic compounds, as we know, the heteroatoms could be halogens, sulfur or oxygen, or nitrogen and phosphorus. And halogens, I have said, fluorine, chlorine, bromine, iodine. These are the mostly heteroatoms that are there, that are present in organic compounds. So this, let's see this formula again, CH3, CH3, and this is OH, heteroatom is there. This group, functional group is called alcohol, and this compound is called alcohol, alcohol functional group. This is also called functional group, and functional group means what? Any heteroatom that is there in organic compound, and the group that is associated with that heteroatom is called the functional group. And we will see what is a functional group in details later. But you should understand that anything that is there with the heteroatom, that we call, and any group, a smaller group associated with the heteroatom, that is OH group here. It's a functional group. Similarly, one can have CHO group, CO group, COOH group. So this kind of groups we see, and in different ways, they are all functional groups, and functional groups actually determine physical and chemical properties of organic compounds, and those things will come later on in the same chapter. So let's see this CH3, CH3. Means one can condense this in this form CH3 twice, because two CH3 are there. And why CH3 whole twice, like this representation will show, because two CH3 are same groups. And subscript 2 we are writing to show this group is has come twice, and they are attached on this CH group. And then CH means these two groups are attached to this CH, and then one can write OH in the similar way. This CH3CH and OH here. Or one can write this also as I said here CH3CH bracket CH3CH3. Or the similar thing we have written here CH3CH, and instead of CH3 OH is here. So OH in parenthesis then CH3. So CH3CH OH CH3. This is also another condensed structural formula, condensed structure. Another way I have, as I have said, CH3 twice CHOH. This compound, the condensed formula will be CH3 thrice CH. That will be enough. And this compound, let's see, this is CH3, CH2, 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 CH3. One can condense this in this form because CH2, 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 three CH2 groups are there. So CH3 will write, then CH2, and the CH2 group has come three times, so we will write thrice, then CH3. Means three here we write as a subscript. So these are the ways, and while writing the condensed formula, some ways you will develop the understanding of this representation even in a better way. So now what we do, even writing these things is sometimes you have to write some atoms and how based on that balance is CH3, CH2, CH2. I mean this way. Sometimes it is difficult. So what people have even developed some another way of representation of organic compound where you have to just draw certain lines and few atoms you have to show. That's all. And drawing lines, it is very easier for us. So for further simplification, organic chemists use bond line structural representation, and that is what the third structural representation, bond line structural formula or bond line structural representation, in which only lines are used. And where we only use lines other than some heteroatoms. Whenever the heteroatoms are there, we show those heteroatoms as well. So in the bond line structural representation of organic compounds, what is we do? Carbon and hydrogen atoms are not shown, and lines representing carbon-carbon bonds are drawn in a zigzag fashion. So in that bond line structural representation, what do? We draw lines, and in those lines we don't show carbon and hydrogen atoms. This is what is based on what people think, that this person has certain understanding of the tetravalency of carbon atom. And if the carbon atom is there and there is no heteroatom, it means all the valency of carbon should be completed because of the hydrogen atom other than the bond that is already shown in the bond line representation. It means what I mean to say, the example you can see here, like this example. See four lines. Four lines means what? There is a single bond between this, all the corners it represent, or all the ends represent some. These are two ends. So this all the corners represents, or all the bends you can say. All the bends represent there is. It means there is a carbon atom, and this there is a one carbon atom here, one carbon atom here. It means there is a single bond. If there is one line, it means single bond is between these two carbon atoms. And this carbon atom has one bond because of this carbon atom. It means its three valency of this carbon atom is not completed. So those three valency must be completed because of the hydrogen atoms. It means there must be three hydrogens associated to this carbon, and that you see here CH3. And at this point, what we see, there is a one single bond with this carbon atom, and there is one group here attached, there one band here as well. So one bend is here, it means there is one other carbon atom here. So there is a single bond again. So one single bond with this carbon atom, one single bond with this carbon atom. So this carbon atom has two CC bonds. It means it will require only two hydrogen atoms to have its valency completed. So it means there is two hydrogen atoms here, means this is CH2 group. So CH2 group you see here. Similarly, CH2 will be here and CH3 will be this. In this formula, what we see, double bonds. If there is a double bond, we will show two lines there. So double lines will be there. So when the two lines, if there is a triple bond, we will show three dash, three lines. So two lines, it means what? It means this carbon atom has a double bond with this carbon atom, and so only two hydrogen atoms are required to complete the valency of this carbon atom. So C, it must be a CH2 group, and so you see CH2 group is here. And at this point, what happens? A double bond with this carbon atom, a single bond with this carbon atom, three valency is already completed with two carbon atoms. So it requires only one hydrogen atom, and you see this CH. And this is CH2 because one double bond here and one bond because of this heteroatom OH group, the functional group. So one bond with this oxygen atom, a functional group, or and this one bond with this. So this carbon already has two bonds. The two bonds of this carbon is shown. It means it also should have a two hydrogen atoms to complete its valency, and so you see two CH2 group. Let's read out what is it. So and what we saw, all these atoms we saw in the lines in zigzag manner. Why we saw these lines in zigzag manner? Because if you don't show it in one line, it will confuse us with a single bond, a one bond. Even if a line is this long or if this line is this long, you will, if it is a straight line, you will confuse with a single bond, one bond. So that is why to just we use zigzag fashion, this fashion we use to show there are different at different bends there are carbon atoms that are present, and there should not be any confusion, and to remove that confusion we use these lines in a zigzag fashion. Now only atoms especially written are heteroatoms, and especially written atoms are heteroatoms of functional grouping and all. And these heteroatoms, we know what are these heteroatoms, atoms other than carbon and hydrogen. It could be oxygen, halogen, nitrogen, sulfur, phosphorus, and so on. The terminals, and this is one thing, usually the terminals means ends of this denote CH3 group, as we saw here. This terminus, if this is a CH3 group, this is CH3 group, if there is no double bond. So this terminus represents CH3 group. That is not important to remember because I have shared you the things that is required for a complete understanding. Groups, unless what indicated otherwise by a functional group or a double bond or triple bond, while the line junction, the line junction or the bends that I say, wherever these lines are joined together. So line junctions denote carbon atoms bonded to appropriate number of hydrogens required to satisfy the valency of carbon atoms. So this junctions is bends represents carbon atoms. So everywhere you see, and if nothing is shown, it means there is a carbon atom. So one carbon, one carbon, one carbon, one carbon. Here carbon, 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 and since here the heteroatom is shown, this functional group is shown, so this is OH group here. And in this compound, what we see CH2, 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 this is a cyclic compound. This we call a cyclohexane. If you know this, because six carbon atoms are there and cyclic compound, so we call six carbon atoms, and saturation is there, so hexane, it is hexane. And since the ring is there, cyclic form is there, so we call cyclohexane. And the bond line representation will be this. And this representation means at each bends, each junction, there is a carbon atom. Carbon, 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 and what we so each carbon has a single, two single C bonds with the neighboring carbon atom. So this has one single bond with this atom, this atom. This will have one single bond with this carbon atom, one single bond with this carbon. So this thing we see, it means each carbon atom has is attached to two different hydrogen atoms. So this is CH2 group, CH2 group, CH2 group. Means two valency because of carbon atoms, and two valencies will be completed because of two different hydrogen atoms, and that we see here. And this is also a bond line representation, and this bond line representation, what we should understand, each carbon, this should be CH2 group, this also should be a CH2 group, similar to this one. This is CH2 group, this is CH2 group, this is CH2 group. You can see here. This is the chlorocyclohexane, and what we see at this junction, this carbon is attached to or linked to this carbon atom through a single bond, and this carbon atom is also linked to this carbon atom through a single bond. And what we see, there is a single bond between this carbon atom and this chlorine. So three bonds of this carbon atom is already shown in this structural representation. It means only one bond is missing, which is not shown here, and that bond must be completed because of hydrogen atom. And that it means this carbon should have one hydrogen atom, and you can see here CH group. Similarly, and some other representations may be the cyclopropane. You can see the cyclopropane CH2, CH2, CH2 group. This is cyclobutat 1,3-diene or cyclobutat 1,3-diene. A 1,3-diene means what? Each carbon atom should have a CH group. Why? Because if I see the CH carbon atom, there is a double bond with this carbon atom. So two valencies here, one valency because of this carbon atom. Each corner has a carbon atom, and it means three valencies of this carbon atom is already completed because of CC bond. So only one hydrogen atom is required now to complete the valency of this. Which means it must be a CH group. We see similar story at this end because double bond here, single bond here at this end also, one double bond and one single bond, three bond. So all the corners of this cyclobuta-1,3-diene should have CH group. Now this cyclopentane is the structure, and what we see here, this is a CH2, CH2. This should also be a CH2 group. What we see, the difference is here and here at this point. And why CH2? Because we see the one bond here, one bond here, CC bond. So the two CH bonds are required to complete the tetravalency of this carbon atom. Now at this junction, what we see, this carbon atom has a triple bond with this carbon atom, and this carbon atom has also a single bond with this carbon atom. It means the tetravalency of carbon is already complete. Three bonds here and one bond here. So four valency tetravalency. It means there should not be any hydrogen atom. There is no place for hydrogen atom at this junction, and similarly at this junction also there is no place for hydrogen atom. So we do not need to write any hydrogen atoms here. So there is no hydrogen atom actually. But in that case, what one should have, one more understanding is required. One more important point that is required here is, usually what we see, that if there is a triple bond, it means the sp hybridization is there, and if there is sp hybridization, these bonds should be at 180 degree, because hybrid orbitals should be at sp hybrid orbitals are arranged 3D space at 180 degree with each other. So there should be 180 degree angle between this and this bond, and you can understand this bond. So 180-degree angle, and that 180-degree angle, if this is a cyclic structure, it will not be maintained. It means there will be a strain in this molecule, and because of that strain, this molecule is not stable. This is not an stable molecule, and this kind of understanding one should have. Similarly, in the cyclopropane, what is if this is CH2, CH2, CH2? What do we know? If the CH2 group is there, the hybridization of this carbon atom will be sp3 hybridization, and if it is sp3 hybridization, then there should be 109.28 degree angle between this group. This CCC bond angle should be around 109 degree. But what we see, this is a cyclopropane. It means it is a equilateral triangle, and it is in this equilateral triangle, this angle is only 60 degree. If this angle is only 60 degree, and we should ideally be around 109 degree, it means there will be a strain in this molecule as well. So this kind of things one should have, and we will see similar examples later on also in this chapter or even in the other chapters of organic chemistry. Now let's see some other examples, and this example is what? The methyl octane. This is methyl octane. This is a methyl, 3-methyl octane. This 3-methyl octane. Octane means we know, octa means 8, and 8 means there must be 8 carbon atoms here in the longest chain, and 3-methyl at third position there is methyl group, and this is the IUPAC nomenclature. We will see this nomenclature later on. So this is one compound, one can simply understand this is one organic compound, one carbon containing compound, or this is a hydrocarbon because we have only carbon and hydrogen atoms in this compound. This is a hydrocarbon, and what we see, this is one representation, and one can also represent the same compound in this fashion, the CH3, CH2, CH2, like this in zigzag fashion, the bonds we are showing, and this at this place will be CH, then CH2, then CH2, 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 CH3, and usually there is certain angle between this angle should not be 180 degree as it is shown here, and usually in the complete structural formula we show here there is a 90 degree angle between this and this in this representation, but in reality there is this angle is 109 degree 28 minutes. It is not 90 degree angle, but this is some angle we represent. So here there is certain angle, and this zigzag fraction, and now all the hydrogen and carbon atoms we may remove this further representation, and that is what we call the bond line representation. And in the bond line representation, we show the terminal atom. If there is no heteroatom, terminal, no double bond or something, no unsaturation, then we show this as a CH3 group. There must be a CH3 group at the terminus. So three terminals are here. This, and this. Here also CH3, CH3, CH3. And the unsaturation, saturation, for you should understand, saturation means all the carbon valency, tetravalency of carbon is completed because of CH bond, then such compounds, organic compounds are called saturated organic compounds. And if all the valency of carbon atoms is not completed because of the single bond, then such compounds are called unsaturated compounds. This means if the compound has double bond, that is an unsaturated compound, because the saturation is not because of the hydrogen atom or some other atom. So that is the unsaturated, this is the saturated one. And the unsaturated compound means if the compound has a double bond like this compound, the unsaturated compound. This compound also has a double bond, but that we will see what is this compound about. This is a functional group. This CO, the heteroatom has come, and because of the heteroatom, as I have seen, this group will be called a functional group. And so anyway, so this is the representation. This is the bond line representation of this compound. And bond line representation, from the bond line representation of this compound, 2-bromobutane. 2-bromobutane, what one can, this means what this group, it means this group should have at this junction there should be a CH group, and in this representation you see CH group is here. Now at this terminus, what should be, this is a CH3 group, because there is this carbon atom and this carbon atom has only one CC bond. It means there should be 3 CH bonds, and to have 3 CH bonds, there must be 3 hydrogen atoms associated to this carbon, and there is CH3, and similarly here should be CH2 and CH3, we know, and this is one representation. Now one can also represent this compound in the condensed form, and the condensed form is this CH3, CH, Br, CH2, CH3. You see here CH3, CH, Br, CH2, CH3. When this Br is written, it means this Br is attached to this carbon atom, not this carbon atom. And if this Br was written before this carbon atom, it means this Br was part of this carbon atom and not this carbon atom. So whenever these heteroatoms are written, usually heteroatoms are written after the carbon atoms. Whenever it is written certain carbon atom, this heteroatom is linked to the carbon atom which it followed in the condensed representation of its structure. So this Br is belongs to this carbon atom and not this carbon atom. This is what you have to remember. Now in the cyclic formula, again this kind of a structure, bond line structure that we have seen. This example we have already seen earlier. This example you see, this example, similar examples we have seen. So I don't think I need to explain this thing again. Now let's see this some questions to expand each of the following condensed formulas into their complete structural formula. Condensed, these are condensed structural formula: CH3, CH2, CO, CH2, CH3. One thing is to write the structural formula is based on the understanding of organic chemistry or understanding of tetravalency of carbon, and can write to have it write it clearly. What we do, we first write all the carbon atoms that are there. So carbon, then carbon, 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 and what we see, and first we write one single bond with for all the between all the carbon atoms. One single bond. If there is a double bond, that double bond we may write make the single bond as a double bond or triple bond later on. So we first write all the carbon atoms with 1, 2, 3, 4, 5. 5 carbon atoms are there. We first to write all the 5 carbon atoms to make a single bond between all the carbon atoms. Then you go to other groups which are attached to each carbon atom. Now what we see, 3H3 atom, hydrogen atoms are attached to this carbon. It means now we have to show these 3 hydrogen atoms on this carbon, and this hydrogen, hydrogen, hydrogen. Now I count how many valencies of carbon is complete here. All the 4 valencies are there, 3 hydrogen and this 1 CC bond. So I don't have to make this bond a double bond. So only single bond will be there. Now I'll come to this. This is CH2. So I write 2 hydrogen atoms. This, and now I count what what is the how many bonds are there with this carbon atom. So the valency of this covalency of this carbon atom will count, and the one carbon double single bond here, one single bond, one single bond, one single bond. This is also tetravalent, so we also don't have to make anything here, anything, or we don't have to make this any double bond, carbon carbon bond as a double bond. Now we will move to this carbon. This carbon atom is associated to one oxygen atom only, and this CO means this oxygen is linked to this carbon atom and not this carbon atom. So we will make one oxygen atom, a single bond will make first, and then we will count the valency and valency of each atom. So what we see, oxygen's valency, usually oxygen has two covalency it shows to have its octet complete, because this atom also follow octet rule strictly, and so it means oxygen, there is no other atom linked to this oxygen atom. Then it means there must be a double bond between this carbon and this carbon. So we will make a double bond here. So the C double bond O we write. And if this was OH group, suppose if this was OH group, so only initially we have written single bond between carbon and oxygen, and this valency, another valency of oxygen is now completed because of the hydrogen atom. Means there will be only one single bond between the carbon and oxygen if this oxygen was OH group. But this is not OH group, this is double bond, so we will have to make a double bond here to complete the octet of this oxygen atom. Now we'll count the total number of bonds that is associated with this carbon atom, and we see two bonds, one bond, one bond, four bonds. So tetravalency of this carbon is also complete. So now we will move to next carbon atom. This is has two hydrogen atoms. Hydrogen will make two hydrogen atoms here. We count valency, covalency 4. We will move to next carbon atom. This is associated to three hydrogen atoms. Three hydrogens we will write, and so we reach here the tetravalence is complete. So this is what we call the complete structural formula from, and this we move from the condensed formula in this fashion. For this compound, this is also a condensed formula, or maybe one may not represent this double bond. Even if one do not represent or do not write double bond between them, then you should also have the understanding that one should write this condensed formula in similar manner, or means a structural formula, but usually people write double bond between carbon carbon atoms, or a triple bond is there. People usually write a double bond and triple bond there. But even if it is not written, you should have this understanding that means there should be unsaturation double bond, because this carbon atom associated to one carbon, this and another carbon here, and one hydrogen, only three valencies. There should be one, but it means this carbon should have a double bond. But that double bond cannot go this side, because valency, tetravalency of this carbon was already complete because of one carbon carbon single bond and three different hydrogen atoms. So there this double bond will go only this side, and that one can understand also, because this is CH and 2, and this CH2. There is one CH2 group, another bond, so there should be a double bond. And this is a CH2, CH2, CH2. This CH2 thrice is what? CH2, CH2, CH2. So we will write, first we will expand this condensed formula, and in expansion what we will write in the CH3, CH double bond, CH, then CH2, 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 CH3, and then we'll write the structural formula. And in the structural formula, then what we'll first see the how many carbon atoms are there in this compound. 1, 2, 3, and 3 carbon atoms here, because this group is thrice. So I had come 3 times in the structure, real structure. So 3 carbon atoms here, 3, 3, 6, and 1, 7. So we'll first write 7 carbon atoms, and we will link all the carbon atoms with a single bond first. So single. So you see 1, 2, 3, 4, 5, 6, 7 carbon atoms, and we'll first write single bond. Then we'll move to other groups which were linked to carbon atoms, and here 3 hydrogen atoms are there. So 3 hydrogen atoms. So these 3 hydrogen atoms must be linked to this carbon. So these 3 hydrogens will write H H H. Now we count the covalency of carbon atoms 4. We'll move to next carbon atom. We'll move here. This carbon atom is now linked to only one hydrogen atom. So we'll write one hydrogen atom. And now we count the covalency. So there was initially we have written only single bond between this carbon atom, and this single bond. And there is one hydrogen here. And so only 3 bonds of this carbon atom is complete. And so what do we do? Then we make this bond as a double bond, because this bond, this carbon atom was already, its tetravalency was complete. We cannot make this bond a double bond, because then in that case this carbon will have a pentavalency, which is fundamentally wrong. So we cannot make this carbon as pentavalent. So we'll make double bond in this case. If we make this single bond a double bond, so one extra dash will write, we'll put there. Then we'll count the carbon covalency, the 2, 1, 1, 4. So now we'll move to next carbon atom. Next carbon atom, this one is double bond is already here, one single bond, 3 bonds and one hydrogen atom was there. The one hydrogen atom will be attached. Then CH2 group. This was the CH2 group. 2 hydrogen atoms, you write CH2 and you count the covalency 4. Then again HH, you count covalency 4. This is what. Next we will move to the this terminal atom, and this terminal atom, what is the CH3, means 3 hydrogen atoms are linked to this. Hydrogen atoms will be right, and then we count covalency, it is again 4. Now it means the complete structural formula for this compound is also written now. Now let's see this question. For each of the following compound, write a condensed formula and also their bond line formula. The condensed formula first we have to write, and then also we have to write bond line formula. This is also represented. This is also one kind of condensed formula, but we can further condense it. And how will we condense this condensed formula? Again, further condense. I will see this CH2, CH2, CH2. 3 CH2 groups are there, so one can write CH2 thrice. So HO, CH2 thrice, one can write. Then CH, CH3, CH, and now this CH is at this terminus attached to one CH3 and another CH3. So one, what can we write? These two groups are linked to this. This parenthesis means this group is linked to this carbon atom. If the carbon or something is there, then you only write parenthesis, because there is CH3 group here and this CH3 group here. One should not get confused that this CH3 group is between this carbon atom and this carbon atom. If it is in parenthesis, it means that this CH3 group is linked to this carbon atom, and not it is not linked to both the carbon atoms. It doesn't come between these two carbon atoms. Instead, this carbon atom is linked, or the CH3 group is linked to this carbon atom, which it followed in the structural formula. So this is CH3 group, and this was actually CH3, CH3, CH. So these two CH3 one can write as CH3 twice. So CH3 and then twice, because two CH3 groups are linked to this CH group, and so this CH3 twice one can write, and this is one condensed formula. And now, and one can also say it a condensed structural formula, because this is a structure that we are showing, or the condensed formula. This is not the molecular formula. Molecular formula will count all the carbon atoms, all the hydrogen atoms, and this heteroatom, and then we represent all this. Like what is here? 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon atoms, 3, 8. Hydrogen atoms will be what? It will be 18. You count 3, 3, you count, it will be 18 and then O. So this will be C8H18O is the molecular formula. Now let's move to then the condensed formula. We can write condensed formula as well. So what we will do, each carbon atom will write in this form. At the heteroatom we also write the hetero group. This is the OH group. The OH group we first write, then we make one bond, and then we make another line with certain angle, and this line, this junction will represent this carbon. This HO group we write. Then another bend to represent this bend with this, then another bend, and this way we represent all the carbon atoms. And here what we see, at this junction, this point, this carbon is linked to one carbon atom here and one carbon atom here and one CH3 group. So this carbon should have the one CH3 group shown in this way. I hope it is clear. Like means if you reach here, it means if you reach here. So, or maybe to write this, what we first do is we write all the carbon atoms that is there in the chain. So C, 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 C. These are the two side chains. This is side chain. This is side chain. And whatever carbon this side chain comes, we write one line opposite. Usually we write opposite to each other if they are on the adjacent carbon. The region we will see later on, but that we write in this way, and this HO group is further attached to the first carbon atom. This carbon atom, the HO group we write here. Now this example what we see NC, this is the cyano group, CN group, this is also CN group. Two CN groups are attached to this CH, and OH, one OH group is also attached here. The OH in parenthesis means this OH is linked to this CH, and it means there is one OH bond in this way. And so what we can write, this a condensed formula as what? This is NC, this is CN, this is also CN, so two CN groups are there, so we can make this as CN twice, and this is CHOH, one can write, or maybe one can write initially OH, CH, CN twice, or CN twice, CHOH. Anyway, one can write, it means all the formula are same, so we write usually HO, CH, CN twice, or CHOH in parentheses, then we have to write again CN twice. And writing two parentheses are not, it doesn't look good because OH we should also write. So what we do, we bifurcate it. The HO group we write before CH means there is only one carbon atom, means this HO will also be associated with this one. If there was another carbon atom here, then we may not write this OH here. Then we have to show this OH to the right hand side. But since this molecule has only one carbon atom, so this HO group we can show even on the left hand side of this carbon. And then the bond line formula will be what? One carbon atom, another carbon atom, another carbon atom. This carbon atom, what we see, this is the only one carbon. These carbon atoms I can show as a group, although they are carbon atom, but they are functional groups, they are groups because the heteroatom is linked to them and directly. So this is the one group, this is one group, one OH group, so only one carbon atom, and then this carbon atom is linked to one CN group, then another CN group, then one OH group, and this is what will be the bond line structure of this compound. Let's see this question. Expand each of the following bond line formulas to show all the atoms including carbon and hydrogen. So these are the bond line structure that is given, and with the bond line structural formula we have to show the complete structural formula. And what we see here, this is C, all the bonds, and what we know it means this is CH2, this is CH2, this is CH2, this is CH2, this is CH2. But at this junction, what we know, this there are three carbon-carbon single bond. It means there is one CH group here only. This at this place also one carbon-carbon bond, one carbon-carbon bond, one carbon-carbon bond. So there is one CH. This only one hydrogen atom is linked to this carbon atom, and there must be three hydrogen atoms linked to this carbon atom because there is only one CC bond, and this three hydrogen atoms should also be linked to this because one CC bond is only there for this carbon atom. Now we know CH2, 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 CH, CH, CH3, CH3. Now all the atoms we know. In the next step, we can show all the C hydrogen atoms with the bond with the carbon atom, and that is what we write. This carbon atom has two hydrogen atoms, so two CH bond will show. So CH bond will see. This carbon atom also has two hydrogen atoms. So two CH bonds we show here. This carbon atom also has two CH bonds. We show it here. This carbon atom also has two CH bonds. You can see CH. This carbon atom has only one CH bond. This only one hydrogen atom was there, so we show only one hydrogen CH. And then this carbon atom also has only one hydrogen atom, and rest of the bonds we will show anyway. So CH3 we show, one CH bond we show, and this CH3 we can write CH in the complete structural formula. We write CH. Here also CH bonds, and this way one can write the complete structural formula of this compound. Now, for this compound, what we see, this compound also, this is one carbon atom at all the junctions. There are carbon out and the terminus there are carbon atoms. So this there is one carbon atom, all the carbon atoms at all these junctions and the terminus. And then we look at the valencies of the carbon atoms in this structure, and we see here carbon only one carbon bond. It means there are three hydrogen atoms linked to this carbon atom, because the tetravalency of carbon should means the four valency of carbon atom should be completed, and that is what the three hydrogen atoms. So we'll write CH3, this is CH3, and similarly this will be CH2 because one CC bond is here, one CC bond is here. So 2 CC single bonds means 2 valency. There are only 2 hydrogen atoms are required to complete the valency of this carbon atom. Means this is the CH2 group. So similarly, CH2, 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 and like this one, there will be CH3 group at this terminus. And now in the complete structural formula representation, what we do, we show all the CH bonds, and that CH bonds we can write. And how will we write? We first look at 1, 2, 3, 4, 5, 6, 7, 8. So these are the open chain compounds. So the 8 carbon atoms we will write, and with 8 carbon atoms single bonds, and later we add hydrogen atom to complete the valencies, as I explained earlier. So this compound, there is a triple bond here. The triple bond here, and then it means there is one bond and triple bond. With the triple bond that we see, we do not show any band in this in the zigzag fashion. Why we do not show a band? It means there is a carbon atom here. We do not show because this is sp hybridized carbon atom. Sp hybridized carbon atom. It means this, there should be 180-degree angle between this. And this carbon atom is also sp hybridized, and we know its valency, 3 valency is here, and 1 valency, 1 hydrogen is required to complete the valency of this carbon atom, this hydrogen atom. So CH bond and this triple bond should, this is also sp hybridized, there should also be 180-degree angle. Anyway, so that because this one should have 180-degree angle, that is why we do not show any bend here. But even though if we do not show any bend, but because of the triple bond, we should have this understanding that there is a carbon atom here. So one carbon atom here, one carbon atom here, one carbon atom at this junction or bend, this one carbon atom here, one carbon atom here. This is also a junction, and that junction is distinct, can be distinguished because of this, the presence of this triple bond. So now what we see, the carbon atom, this carbon atom requires one hydrogen to complete its valency. So we write HC, then triple bond, we will write then this carbon atom does not require any hydrogen atom because 3 valency is this, and 1 single bond. So tetravalency of carbon is already complete. So this carbon should not have any hydrogen. So we do not show any hydrogen to this. And then we move to this. This is CH2 group because this is a single bond. This is a single bond. Carbon carbon single bond. 2 valency, 2 hydrogen atoms are required. So that is this CH bond here. So CH we show here. And then this is also we move here. And at this, what we know, one bond this CC bond, one CC bond this, and one CO bond, single bond. So 3 bonds, so 1 hydrogen atom should be here. So we show 1 hydrogen atom here. So C. So an OH group and 1 hydrogen we write above. And to write this again, what I have seen earlier, you write first, you count number of carbon atoms, 1, 2, 3, 4, 5 carbon atoms. You write all the 5 carbon atoms in a line, and you first write if there is a double or triple bond shown, you write double or triple bond, and if it is not shown, then you first write single bond, and then based on the valency and the number of hydrogen atoms that are present there, based on that you can add hydrogen atoms and to complete the tetravalency of carbon. That understanding is anyway that is associated with this kind of representation, and this is the what, this is a bond line representation to complete the structural formula we are writing. So in the bond line representation, as we know, the double and triple bonds are already shown, and since we know where is the double bond and triple bond, we can directly write double bond and triple bond. In the condensed structural formula here, we do not know where is the exactly the double bond or triple bond, it comes or not. If it is shown, you can write double bond or triple bond directly. Here it is shown, and if it is not shown, as I said, it may not be shown in some of the condensed formula that there is a double bond between these 2 carbon atoms. So you can write write this as CH3 CH and this group later on, and there you have to make understanding that there is a double bond between this CH group. That is why I showed. And but if the double bond is shown, most of the cases we show, but then you can directly write the double bond there. In this case, double bond CO double bond, there is a carbon oxygen double bond that is not shown here. So you have to make out there is a double bond between this carbon and oxygen based on the understanding of valency of carbon and oxygen. That is what, and there triple bond is shown, and then COH and these kind of things. I hope it is very clear to you. Now in this form, this D, and this is what, this is a CH3 group as we know. There is one bond, the CH3, CH3, this should be CH group. Why? Because one CC bond, one CC bond, one CC bond. So one hydrogen is only required to complete the valency of this, tetra valency of this carbon atom. So this is CH, this is also CH, this is CH3, this is CH3. And now you can open all the CH bonds to write the complete structural formula, that is here. So this CH3 one can write H, H, H. This carbon H, H, H. This H. Then similarly H, 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 CH, CH, CH. Here CH, 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 and the CH bond is already shown. So that will be a complete structural formula that one can show in this form. And I hope this point is this kind of things you are able to do. You will be able to do this kind of conversion, condensed represented or condensed formula to the bond line structural formula, or bond line structural formula to complete structural formula. These are a kind of things you will understand, because sometimes in some cases see this representation is shown, sometimes in this representation questions are asked, sometimes in this form also molecules are or organic compounds are shown or represented in questions. So all these formulas or all these representations you should understand. But one point is later on in higher studies or in organic compound, we mostly use this kind of representation because it is easier to write this representation, because you have to make just lines, and based on the lines and right understanding of how many hydrogen atoms will be there, that is already there with this bond line structural formula, until unless there is another term that comes stereochemistry, and this what is stereochemistry and the stereoisomerism, that we will see when we will study isomerism later on. So then only we show something, and the 3D representation of this organic compound. So what is the 3D representation? These things we'll see in our next class. I'll stop here. I hope this representation of organic compound, this thing is clear to you. Good day once again. Happy New Year to all of you. Bye.